To begin this note, I just wanted to remind you that when you multiply a scalar or just a number or a value by a vector, you get a vector. I'm just going to begin by going through the definition of a collinear vector. So we can say that two vectors are collinear if they lie on a straight line when arranged tail to tail. These vectors are scalar multiples of each other, meaning that they are parallel. What you see now are three statements, and these statements are all equivalent. So if we say that one of them is true, we're automatically implying that the other ones must also be true. So these following statements about two non-zero vectors, vector u and vector v, are equivalent. The first one says that vector u and vector v are scalar multiples of each other. So vector u is equal to some scalar k times vector v, where k is an element of the reals. The second statement says that vector u and vector v are collinear. And the third statement says that vector u and vector v are parallel. Next, we're going to discuss a few properties that we're going to be using when we're talking about scalars and vectors. So the first is the distributive property. So for any scalar k, which is an element of the reals, and any vectors u and v, k, so a scalar k times, in brackets, vector u plus vector v, is equal to that scalar k times vector u plus that scalar k times vector v. The next property that we're going to be discussing is the associative property. So this property is involving multiplication again. For any scalars a and b that are both an element of the reals, and any vector v, the scalars a, b times vector v is equal to a times the scalar b times vector v. So basically, it doesn't matter the order that you multiply these, you will get the same result. The last property that we're going to be talking about probably will seem very silly and obvious to you, but we're going to put it here anyways in case you ever need it. So the last one is the identity property. So for any vector v, 1 times that vector v is just equal to that vector v. Alright, so one quick thing that I wanted to mention before we start into our examples. Given two vectors, vector u and vector v, and two scalars, s and t, which are both elements of the reals, the quantity s times vector u plus t times vector v is called a linear combination of vector u and vector v. Alright, so example 1. In trapezoid ABCD, side length BC is parallel to side length AD. So I'm going to go ahead and I'm just going to put that in there. And side length AD is 3 times the length of side length BC. So it doesn't really look like that in my diagram, and I'm really sorry it's not to scale, but we're going to pretend it looks right. We have vector u equaling AB. So this is vector u, and vector v is equal to BC. So this is vector v. Express AD, BD, and CD as linear combinations of vector u and vector v. I'm going to start out with the easiest one first. So we're going to do AD right now. So vector AD, we know in the question it told us that it's 3 times BC. Now if I look at my diagram or in the question, we know that BC we called vector v. So AD is equal to 3v. And he is done. So the next vector that we're going to do is vector BD. Now we know from previous lessons that I could rewrite vector BD as a linear combination of BA plus AD. Now when I look at BA, I know what that is. So I know that AB is vector u, so BA is just negative u. And again, I also know AD. I found it above. I know that AD is 3v. So vector BD is equal to negative u plus 3v. So my last vector is vector CD. So I basically need to figure out what the path is that I need to take if I want to create this vector. I'll highlight it in yellow from C to D. So I want to start at C, and the first thing that I'm going to do is I'm going to have my CB. So again, I'll highlight it in yellow. We're going to start here and we're going to go here. Next, I'm going to add this vector BA. And then finally, I'm going to add the vector AD. Now, I know that I can rewrite these in terms of U's and V's. So vector CB is negative V plus vector BA is negative U plus vector AD, which is 3v. Just like when we combine like terms, I can simplify this a little bit. So I have the negative v plus the 3v. That will give me 2v, and I have the subtract u.